Alright, so welcome back to this class video. In this class, I'll be taking you guys rotational motion, which is a particular topic in physics 101. Okay, so this class video is divided into 5 parts. First part, we talk about definition, whereby I do definition whereby we define rotational motion, we differentiate it from circular motion. Second part, we talk about rotational analog. The third part, we talk about moments of inertia of different bodies. This part is very important. The fourth part, we'll talk about radius of gyration. While the last part, we'll do questions and answers relating to this topic. Okay, so what is rotational motion and what is circular motion? What is the difference between, because these two types of motion, rotational and circular, they are two different types of motion. Okay, so what is rotational motion and what is the difference between rotational motion and circular motion? Now, rotational motion is the type of motion whereby an object revolves around its own axis. Okay, this is very important. Around its own axis. Okay, very important. Okay, then in circular motion, the object revolves around a fixed point in a circular path. Okay, so in rotational motion, the object revolves around its own axis, whereas in circular motion, the object revolves around a fixed point in a circular path. Okay, both are circular motion. Both are motions in a circular path, but the object revolves around its own axis, while the other one, the object revolves around a fixed point in circular path. Now, another difference between rotational motion and circular motion is that in rotational motion, the axis of rotation, okay, the axis of rotation lies inside the object. This is very important. Okay, that is in rotational motion. The other difference, the axis of rotation lies inside the object. For example, for example, the Earth. We all know that the Earth rotates around its own axis. That is very important, right? Yes. Let's say this is the Earth, for example. Okay. Let me draw it well. I'm coming. Okay, so this is the Earth, right? Yes, this is the Earth, this is the north, and this is the south, right? So this is an imaginary line, right? Yes. So the Earth usually, if you look at it, the Earth usually rotates around its own axis every 24 hours, right? The Earth usually it rotates. The Earth usually revolve around its own axis, right? Yes, every 24 hours, right? Yes. So this type of motion is a rotational motion. Yes, but when the Earth or when a planet revolve, okay, let me just continue first. Okay, so the axis of rotation lies inside the object. If you look at the Earth, for example, look at this is an imaginary this is an imaginary line, or this is an imaginary axis. Okay, so if you look at it, the axis is usually inside the object. Okay, so that is in rotational motion. Okay, yes. Another example is a ceiling fan. Okay, or you can say a fan. Okay, so let's use the ceiling fan for example. Okay, let's say this is 3 blades of ceiling fan, right? Then this will be an imaginary line, right? An imaginary line, which is the axis. So the ceiling fan usually rotates around this axis. Okay, if you look at it, the axis of rotation is usually lies inside the object. If you look at it, okay, yes. So that's rotational motion. Okay, then while for circular motion, the axis of rotation lies outside. Yes, the axis of rotation lies outside the object. Yes, lies outside the object. For example, a vehicle moving around roundabout, right? Yes, let's say this is roundabout, right? So this is the vehicle. Is the vehicle usually rotate? Usually move around what? This roundabout, right? Yes. Is the axis of rotation inside the vehicle? No, the axis of rotation is not inside the vehicle. The axis of rotation lies outside the object. Yes, so this is an example of a circular motion, right? In circular motion, axis of rotation lies outside the object. Apart from that one, objects revolving around the moon revolving around the Earth, right? The moon revolving around the Earth. the axis of rotation is not is the axis of rotation is not um yeah, the axis of rotation is not inside, does not lie inside the moon, right? Yes. So the planet revolving around the sun, planet revolving around the sun, moon revolving around the earth revolving around the sun as well. Vehicle moving around roundabout, all this type of motion is a circular motion because the axis of rotation lies outside the object. So in summary, in rotational motion, the a body rotates around its own axis. Then when it's circular, the object and a body usually revolve or rotate around a fixed point in a circular path. Then in rotational motion, axis of rotation lies inside, while in circular motion, axis of rotation lies outside the object. Okay, so that is all about circular definition of circular motion, different between I mean that is all about the definition of rotational motion, okay, different between rotational motion and circular motion. Now I'll move to um now before I move to this part, let's take up take note of this part, okay. Okay, let's say for example a body is rotating, is revolving around in a circle like this, for example. Now this part here from the center to this point, this is known as what? Arrow is known as the radius of the circle, right? Yes. While this angle, this theta here, this one here is known as this is known as radius, right? Radius of the circle. Then why this one is known as angular displacement. Very important, angular displacement. Okay. Why this one is known as the length of the arc. Okay, length of the arc. Okay, or you can just simply call it linear distance, or okay, this one is just my length of the arc. Okay, calculate distance or anything else. Okay, so this is known as length of the arc, this is known as radius, this is known as angular displacement. So S is known as what? The length of the arc. Arrow is radius, this one is known as the angular displacement. Okay, so that's to tell you that S is equals to what? Angular distance times what? Radius. So this formula is very important, okay. I have cleaned it. This formula is very important, okay. Now let's move to the next part, which is rotational analog, okay. Continue with rotational analog, okay. Yes, so these are the these are the quantities, okay. So these are the quantities, then their linear terms and their rotational analog or their rotational terms, okay. So mass is a quantity, right? Yes, the linear term for mass is still what? Is still mass, right? Yes, it's still mass, right? Yes, mu. Then why for rotational analog, or why for in rotational term, mass is regarded as moment of inertia, which is okay. Yeah, you cannot like I'm coming in the rotational analog of mass is known as moment of inertia, okay, known as moment of inertia, okay. Yes, known as moment of inertia, right? Is represented by I, okay, which is equals to m r square, okay. So quantity like mass, the linear term for mass is still mass, right? Yes, the rotational analog of mass is moment of inertia, which is I, right? Moment of inertia is equals to mass of a body times the square of the radius, okay. Yes, then displacement in linear term is still known as what? Still known as displacement, right? Yes, in linear term or in linear motion, it's still known as displacement represented by S, right? Yes. But in rotational motion, the analog of displacement in rotational motion is angular displacement. Okay, it's angular displacement. Okay, represented by should I just okay represented by this symbol, and is equals to normally we previous like I told you guys that the length of the arc is equals to angular displacement times radius, right? Yes. So if we make angular displacement stand alone, angular displacement will be equals to what? The length displacement divided by what? Arrow, right? Yes. So angular displacement is equals to, this is very important, please take note, is equals to what? S over arrow, right? Yes, it's very important. Angular displacement is still equals to 2 pi radian. Yes, angular displacement is equals to 2 pi in radian. Okay, this is very important. Then we move to the next part, velocity. In linear term, is still what? It's still velocity, right? Yes, still velocity represented by v. In rotational term, or in the rotational analog of velocity is angular velocity. Okay, is angular velocity represented by omega, right? W, or so yeah, W. Okay, we all know that velocity is what? Velocity is displacement, right? Over time, right? Yes. Therefore, angular velocity will still be what? Will be what? Will be angular displacement over what? Over time, right? Yes. Are we done yet? No. Equals to now angular displacement is equals to what? S. Let me just come here. We are okay. Angular velocity is equals to what? Angular displacement over time, right? From linear term, the velocity is called displacement over time. So angular velocity will be what? Will be angular displacement over time, right? Yes. Now, if we check, angular displacement is what? Is S over arrow, right? So S divided by arrow. Then don't forget about what? Our T. So everything multiplied this, we have something like this. S divide ROT, right? Yes. Are we done yet? No. Now, if you look at this, if you look at S over T, or yeah, S over T, which is distance over time, right? Yes, distance over time is the same thing as what? Velocity, right? This okay. Let me okay. This we know that S is what? Is displacement, right? Yes. So displacement over time is known as what? Displacement over time is known as what? Is known as linear velocity, right? Yes. So in the place of, remember, don't forget about this arrow. Arrow was here, right? Arrow is here, right? Yes. So we will be on that displacement divide time will give us what? Will give us velocity, right? Yes. So therefore, to now be all, you will not be what? All will not be v, right? V over what? V over arrow. Okay, yes. Because this displacement over time will give us what? Will give us linear velocity. So angular velocity is equals to angular displacement over time, which is still equals to S. Remember, angular displacement is what? Is this displacement over what? Radius, right? Don't forget about this our time, right? Yes. Now this displacement over time will give us what? Velocity, right? Then divided by this our arrow. So angular velocity is still equals to what? Linear velocity over arrow. Yes. So yes. So in the place, so W is equals to angular displacement of divide time, which is still equals to what? V over arrow, right? Yes. So it's very important. Yeah, let's continue. Okay. Acceleration. We all know that acceleration is what? In linear term, acceleration is still acceleration, right? Acceleration is what? Velocity over time, right? Yes. So in rotational term, or the rotational analog of acceleration is known as what? Is known as acceleration, right? It's known as angular acceleration, which is presented by this symbol, right? Yes. So if linear acceleration is equal to velocity over time, therefore angular acceleration will be what? Will be angular velocity over what? Time, right? Yes. So if we continue, let me use it here. Now, angular acceleration will be what? Will be angular display and will be angular velocity over time, right? Yes. Don't forget that angular velocity is what? V over arrow, right? Yes. Yeah, V over arrow, right? Yes, V over arrow. Don't forget about our time. Okay, let me put it like this. Okay, V over arrow, right? Yes. So if we continue, let me see. Okay, yes. If we continue, remember angular acceleration is equal to angular velocity over time, right? Yes. And we all know that angular velocity is what? V over arrow, right? So V over arrow, then this time. Now, if you look at it, V divide time, over T is what? V over T is what? Is linear acceleration, right? So therefore angular acceleration, V over T is linear acceleration, right? So everything here will be what? Will be A over what? Arrow, right? Yes, will be A over arrow. Okay. This acceleration is known as tangential acceleration. So therefore, angular acceleration is equals to tangential acceleration over what? Radius. Okay? Yes. So it's very easy. So angular acceleration is equals to angular velocity over time, which is still equals to what? Which still equals to tangential acceleration over arrow. Yes, this is very important. Okay? Yes. Then what about force? Now, the linear term for force is still what? Is still force, right? It's still force. And remember, force is what? Force is mass times acceleration, right? Yes. In the rotational analog of force is known as torque. Okay? Is known as torque, represented by this symbol. Okay? Yes. Now, if force is equals to ma, therefore torque will be equals to what? Remember, I told you guys that moment of inertia is analog to mass. I don't even understand. Is analog to mass. So if force is equals to mass times acceleration, therefore torque will be equals to what? Moment of inertia times angular acceleration, right? So torque is equals to what? Moment of inertia times what? Times angular acceleration. That is just it, okay? Therefore, if we expand it, we all know that moment of inertia is what? M arrow square, right? Then angular acceleration, right? Yes, so it's very easy, okay? Yes. So that's just it. If we continue, we know that this one is equals to this. So that's why you can write a lot of formula under rotational motion. It's very, very easy, okay? So that's very easy. Force is equals to MA. We all know that one, right? Now in rotational motion, it's not known as torque, right? Yes. If in linear term, force is equals to MA, the rotational term will be what? Moment, because I told you guys, moment of inertia is analog. That is in the mass in rotational motion is regarded as the analog of mass in rotational motion is moment of inertia, right? Since force equals to ma, therefore torque will be equals to what? Will be moment of inertia times angular acceleration, right? Yes. So if we continue, momentum, we all know that momentum in linear term is still momentum, right? Yes. Momentum is equals to what? Mass times velocity, right? Yes. The rotational analog of momentum is what? Is angular momentum. Okay, all this is very easy. Angular momentum, right? Yes, presented by L. Now, if in linear term momentum is equal to mass times velocity, therefore in rotational term angular momentum will be equals to what? Will be equals to what? Moment of inertia times what? Times angular velocity. Because in linear term we know that momentum is mass times velocity. In angular time, in angular term or in angular all right, what am I saying? Yeah, in angular term or in rotational term rather, angular momentum. So it should not be angular momentum, right? Yes, which is L is equals to what? It's not because moment of inertia times angular velocity. Moment of inertia times what? Angular velocity. Yeah, so this is angular momentum, which is equals moment of inertia times angular velocity. This one is mass times velocity, right? In linear term, momentum is mass times velocity. In angular term or in rotational term, it will not be angular momentum, which is equals to what? Moment of inertia, which is analog to mass in linear term. So which is moment of inertia times what? Angular velocity. So if we expand it, it will now be m arrow squared then times what? Times w. You can still keep on expanding, okay? W is this and this, so you can still keep on expanding. Okay, so let's continue. Work. Okay, in linear term, work is what? Is force times distance, right? Yes. In angular term, work will be what? Work will be what? Normally, force in rotational term is what? Is torque, right? Yes. Times distance in rotational term is what? In rotational term, distance is what? Angular displacement. I mean, this is displacement, right? Yeah, force times displacement, right? Yes. So force in rotational term is what? Is torque, right? So that's put it here. Then displacement in rotational analog or in rotational term is what? Is angular displacement, right? Yes. Therefore, work in angular in rotational analog to what? Is torque times angular displacement. Yes. The energy Okay, let me use specifically, let me use kinetic energy. Okay, specifically kinetic energy. Kinetic energy is what? Half ke. Kinetic energy in linear term is half mv square, right? Yes. Therefore, kinetic energy in rotational term will be what? Will be half. Remember, mass in rotational term is what? Is moment of inertia, right? Yes. The velocity in rotational term will be what? Angular velocity, which is W. So therefore, kinetic energy in rotational term is half I W. Don't forget about the square, because this one has square, RW square. Okay, or I omega square. Okay, yes. So this is for energy, okay? So half RW square. Okay, now the last part, force and power. In linear term, power is work work over time, right? Or energy over time, right? Yes. Therefore, in rotational term, power will be what? Let me use this place for example. Power will be in rotational term. Power will be if remember work in this work, right? In linear work in rotational term is what? Is torque times angular displacement, right? Angular torque times angular displacement, right? Yes. Then let's not forget about time, right? Time. Okay. So power in rotational term is what? Power in rotational term is torque. Power in rotational term is torque times angular displacement divided by time, right? Are we done yet? No. Remember, angular displacement over time. Angular displacement over time will give us what? Give us angular velocity, right? So therefore, power will be equals to torque, angular displacement over time. Angular displacement over time. Angular displacement over time is what? Is equals to angular velocity, right? So therefore, power will be equals to torque times what? Angular velocity. Okay. Yes, angular velocity. So power is equals to what? Torque times angular velocity. Yes, very important. So okay, so we are not done. Okay, so these are linear terms, rotational analog in I think so. Yes, so these are linear terms and they are rotational analog in rotational motion. Okay, then there are still few other things I need to tell you guys. So all these are very easy. Okay, another one. Let me just clean this place. Okay, so another one. Few things left. Okay, so we all know that in linear motion, v is equals to u plus at, s equals to ut plus half at square. Then v square is equals to u square plus 2as, right? Yes. Now in rotational analog or the rotational term will now be what? Our v is what? In rotational motion, our v is in rotational analog of velocity is angular velocity, right? Then we put W naught, which is initial angular velocity, then plus acceleration in angular term is angular acceleration, right? Yes, then times time. Then displacement in angular term, displacement, we all know that displacement is this one, right? Yes. Then initial velocity will be what? W and W naught then times T then plus half acceleration in rotational term is angular acceleration, right? Then times T square. The last part, velocity in rotational motion is W square, right? That is omega square, which is angular velocity, which is equals to initial velocity will be what? Angular velocity naught, right? Yes. Then plus 2 acceleration in rotational analog is linear rotational acceleration, right? I mean, it's angular acceleration, right? Yes. Then what about displacement in rotational term or rotational analog? Displacement is what? Is angular displacement, right? Yes. So this is the equation of motion in linear terms. Why this is the equation of motion in rotational terms or in rotational analog? Okay, so all these things are very important. Like these formulas and all. So please take note of the ones I've cleaned and this other one. Please, very very important course, we're going to use them to solve. For example, talk, like it's very, very easy to get. No need to cram. I don't understand. Don't need to cram at all. Remember, moment of inertia is equals to m square, right? Yes, so no need to cram and all. Now let's move to the next part, which is moment of initials of different bodies. All right, so for the moment of initials of different bodies, okay, moment of initials of different bodies. Now, at first, where is moment of inertia? Moment of inertia is just the measure of resistance to rotational motion. Okay, so that resistance, the measure of the resistance. Look at it. The measure of resistance to rotational motion about a given axis is known as moment of inertia. Okay, yes, that resistance of a body to rotational motion about a given axis is known as moment of inertia. Generally, the general formula for moment of inertia, remember, moment of inertia is presented by this symbol. Generally, the moment of inertia or the moment of inertia of a single body or a single particle generally is what? Is mr square, mass of that body times the radius. Okay, that times the square of the radius, right? So this is the general formula for moment of inertia, or you can see the formula for moment of inertia of a single particle. Okay, don't forget that moment of inertia is the measure of the resistance, the measure of resistance to rotational motion about a given axis, right? Yes. Now, different bodies. Remember, moment of inertia of a body is majorly is determined by the mass of that body as well as the radius. Is very important. Okay, yes, very, very important. Okay, so for a single particle or for a single body, moment of inertia is equals to the mass of that body times the radius times square of the radius. Okay, now for a thin rod, for a thin rod, okay, these are the bodies, these are the axis of rotation, these are the moments of inertia. Okay, so for a thin rod, when the axis of rotation is about the center, the moment of inertia of a of a thin rod is 1/12 the mass of that rod times the length times the square of the length. Okay, then for a thin rod again, when the axis of rotation is about one end, the moment of inertia is 1/3 ml square. Okay, then for a solid disc, this is very important. For a solid disc, if the axis of rotation is about the center, okay, so for a solid disc, the moment of inertia is r mr square. Okay, then for a solid cylinder, axis of rotation is about the center. Okay, so for a solid cylinder, the moment of inertia is still what? R mr square. Okay, then for a hollow cylinder, axis of rotation is about the center. For a hollow cylinder, the moment of inertia is mr square, very important. Then for a solid sphere, axis of rotation is about the diameter. The moment of inertia is what? Is 2/5, 2/5 mr square. Okay, then for a hollow sphere, the moment of inertia is 2/3 mr square. So these are the moment of inertials of different bodies. There are more. Okay, I just give you guys these ones. Okay, so these are the moments of inertials of different bodies: a thin rod, a solid disc, a solid cylinder, an hollow cylinder, a solid sphere, an hollow sphere. Okay, yeah, so these are the moments of inertia of these different bodies. Okay, so now let's move to radius of gyration. Then before we move to question, before we move to answering questions and answers. Okay, to this last part, which is radius of gyration. Okay, radius of gyration is also known as equivalent radius. Okay, is a constant. Okay, it's represented by letter K. Okay, that is radius of gyration, or it's also known as equivalent radius. Now, what is radius of gyration? Radius of gyration is that distance from the axis of rotation, the distance from the axis of rotation at which the whole mass of a body may be assumed to be concentrated. Okay, yes, that is known as radius of gyration, which is represented by K. It's also known as equivalent radius, right? Yes, it is the distance from the axis of rotation, okay, at which the whole mass of a body may be assumed to be concentrated. Okay, so that is the definition of radius of gyration. Okay, it's presented by k. It's a constant. Okay, so how can I look for the radius of gyration? It's very easy, very, and this is an exam based question. It's very rampant in exam. Okay, it's very